let's continue our conversation about acid-base equilibrium. So do you remember when I was teaching you to write net ionic and total ionic equation, and I was getting really mad when you were separating water because water was able as a liquid and you never separate the liquid, right? Well, guess what? Actually, water does separate to a little extent. So do you think, don't get mad at me, I wasn't lying to you, it's just that it's an equilibrium reaction, and actually the equilibrium is very much leaning towards water on this side. So let me get the pointer. The equilibrium is very much leaning on this side, and the amount of H plus and OH minus that you have is extremely small. So this process is called self-ionization or auto-ionization of water. And you can write it as just one single molecule of water splitting in two, or to be more rigorous, because this H plus would be such a small atom with a full charge, it doesn't really exist in solution. What happens is an acid-base reaction where one molecule of water acts as a base and the other molecule of water acts as an acid. So the base one has the unshared pair to form a new bond with the hydrogen of the other one that's acting like an acid. And so you end up with a conjugated acid of the base. So this is the conjugated pair, base and acid, and this is the other conjugated pair, acid and base. So if we go and write the equilibrium constant, right, it's once again an heterogeneous equilibrium, because on the reactant side, both molecules that are identical are liquid, so they should not appear in our equilibrium constant. And all should appear are the two products, H3O plus and OH minus. So the formula for this equilibrium constant be quite simple. There are only two factors, and as it happens, the value is a very small value, is 10 to the minus 14. Now, if the only thing that I have in the solution is water, so meaning it's pure distilled water without anything else, the only source of these two ions is the reaction. Every time I make an H3O plus, I'm also making an OH minus. So I think it's pretty reasonable to assume that the amount of one is going to be equal to the amount of the other. Therefore, the concentration of each of them is the square root of 10 to the minus 14, that is 10 to the minus 7, right? At least at room temperature, 25 Celsius, 298 Kelvin. If we change the temperature, things becomes more complicated, but we don't have to worry too much about that. That goes a little bit beyond the purpose of this class. So if the concentration of each of them is 10 to the minus 7, that means that I need to take 10 million molecules of water in order for have one atoms of one ion H3 O plus and one ion OH minus. So it's a really, really small amount. That's why we never mentioned it before. Now, to deal with this number is kind of a pain because they are so small, right? So in general, they say psychology-wise, people don't like negative numbers, especially on their bank account, and they also don't like small numbers. Yeah, it would be nice to have numbers like in a range that's easy to handle, like between 0 and 10, something like that. So we do some manipulation to the concentration to make them more convenient to use. So the first thing when we do, we take the logarithm of the concentration. So the number becomes more reasonable. And because the numbers are very small, the logarithm of a very small number becomes negative, so we don't like that either. So we are going to stick a minus in front of the logarithm to make it positive. So for example, if we have a concentration of 10 to the minus 7, the logarithm of 10 to the minus 7, the decimal logarithm obviously, would be minus 7. And so to get rid of the minus, I stick a minus in front, so minus minus 7 becomes 7. So this is the definition of the pH minus the logarithm of the concentration of the H plus. I can do the P something of anything that I like. So I could do, for example, the POH. That would be minus the logarithm of the OH minus. If I have the K an equilibrium constant, I could calculate the pK by calculating minus the logarithm of that equilibrium constant. So I can calculate the P of anything, basically. So for water, we have figured out that the product between the concentration of the H3O plus and the concentration of the OH minus is equal to 10 to the minus 14. So if we, instead of doing this in the domain of in form of a multiplication, we use logarithm, right? We would have to calculate the logarithm on both sides of the equality. So this would become the logarithm of the concentration, the product of the concentration. That's equal to the sum of the logarithm. So that would be the pH plus the pOH. So what I'm trying to say is that if you're multiplying the concentration here, but because you are taking the logarithm of the product, then you get the sum of the logarithm. So you end up with 14 is equal to the sum of the pH plus the pOH. So this formula, the set of these formulas, 1, 2, and 3, allows you to calculate, to convert from pH to pOH. Depending on the value of the pH, so depending on the concentration of the H plus, we classify solution as acidic or basic. So if the pH, meaning minus the logarithm of the concentration of the H plus, is the same as we have in distilled water, in which case the concentration of the H plus would be 10 to the minus 7, so the pH would be 7. So in distilled water, the pH should be 7. And it would be equal to the pOH, that would also be 7. And the sum of the two would give you 14. If you have an excess of H plus, right, so if the concentration of the H plus goes up, the logarithm becomes a more smaller number. Because let's say the concentration of the H plus is 10 to the minus 3, then the pH is 3. But if the concentration of the H plus is 10 to the minus 1, that would be 100 times bigger, then the pH would be 1, that would be 2 units smaller, right? So that's a bit counterintuitive. So the smaller is the pH, the more acidic is the solution. Now, the vast majority of the solution that you will encounter in your life, the pH is going to be between, acidic, is going to be between 7 and 1. However, a pH could be 0, a pH could be negative. If you have a concentration, a very high concentration of, let's say, hydrochloric acid, if the hydrochloric acid is 10 molar, the pH will come up negative, and we can do some example to see that. So the fact that the pH scale goes between 0 and 14, that refers to the most common value, but there is no theoretical reason why you couldn't have a negative value below here, or you could have, for the same reason, a pH that's above 14 if you have a lot of NaOH. You see here, 1 molar solution of NaOH has a pH of 14, but I could have a 10 molar solution of NaOH, and then in which case the pH would be 15. So for any solution that has a pH above 7, we would say that that solution is basic. And as you can see, the majority of, let's say, bodily fluid and food tend to be in the acidic range. There isn't really much here that we would have in our pantry that would be basic. Pretty much the only thing is baking soda. The human blood has a slight, is close to neutrality, but has a slightly basic pH. But if we want to find example of basic stuff, we need to use basically cleaner, soap, or the drain cleaner. That's pretty nasty stuff. You may end up actually ruining the piping trying to use this stuff, so it's generally not a good idea to try to use strongly basic product down the drain. But yeah, that's pretty much the pH scale. So this is a little drawing that shows you how to convert from concentration of the H plus to pH to concentration of the OH minus to pOH. So from concentration of the H plus to pH, you calculate the logarithm and you change the sign. The opposite procedure is the anti-log. So basically you take it's 10 to the minus pH is giving you the concentration of the H plus. The very similar relation is between OH minus and pOH. The relationship between the H plus and the OH minus is that they are inversely proportional, so their product is always equal to 10 to the minus 14. Between pH and pOH, because you are in the logarithm domain, then it would be their sum to be constant, while here is the product to be constant. So the sum of pH and pOH is always going to be 14. So if I give you the concentration of the H plus and I ask you to calculate the pOH, you have two possible paths that would give you exactly the same result. You could get the concentration of the H plus, calculate the pH, and then subtract 14 from the pH to get the pOH, or you may decide to calculate the OH minus from the H plus, and then once you have the OH minus concentration, calculate minus the logarithm of that. That would be totally equivalent in terms of result. So let's see some example. pH calculation for a strong acid. So they want to know what's the pH of a solution of a 0,15 molar solution of HCl. So first of all, how do you know it's a strong acid? If you've done your homework and you've studied, you should have memorized the 7 or 6 strong acids. So that's one way. If you have, for some reason you have a blank, the fact that they do not give you the Ka, it's inherently suggesting this is a strong acid. Because if it's a weak acid, there would be a mention to the Ka in some shape or form. So this is a strong acid. Calculating the pH of a strong acid is the easiest of the scenarios because it's completely dissociated. Therefore, once I put it in solution, there is no HCl residual. It's reacting in a 1-to-1 ratio. So per each mole of HCl, I make 1 mole of H3O plus and 1 mole of Cl minus. I want to know the pH, so this is the part of the reaction I'm interested in. So it's a 1-to-1 ratio between these two. So if I am dissolving 0,15 moles in 1 liter of water, I would end up with 0 moles of HCl because it's all dissociated. 0,15 moles of H plus and 0,15 moles of Cl minus. So that means that for a strong acid, the concentration of the H plus is the very same number as the concentration of the original acid. So all you have to do is calculate minus the logarithm of 0,15. And that's 0,82. So it's pretty acidic. Let's say that we dilute that acid 10 times. So instead of being 0,15, is now 0,015 molar. So it's 10 times more diluted. What's going to happen? We can calculate the pH with the same procedure. So minus the logarithm of 0.015 is now 182. So you see that by a dilution of 10 times, the pH has moved of a full unit. This is characteristic of strong acid. If you would have a weak acid, by diluting 10 times, the pH would also go up, but not as much, right? So again, the pH is going up, is getting bigger, because the concentration of the H plus is getting smaller. it's a full unit of difference if you have a strong acid, is less than a full unit if you have a weak acid. Also, this is a good opportunity to show you the use of sig-fig with logarithm. So in this case, the sig-fig are determined by the fact that we have 2 sig-fig for the concentration, right? So here you would have not noticed anything weird, but here you would think, why did she use 3 sig-fig? Well, when you calculate the logarithm, the number before the decimal point is not significant. In fact, look at this, you have the very same number, just 10 times smaller. So for the concentration, you express the fact that is 10 times smaller by adding a 0, basically moving the decimal point. In the logarithm domain, you express the fact that it is 10 times smaller by changing the first figure, that's a 0, into a 1. If I would make it 100 times smaller, the pH would be 2.82. If I would make it 1000 times smaller, it would be 3.82. So the first number in a logarithm is not a measurement. It's just telling me how small or how big the number was. It's sort of the equivalent of the decimal point. Therefore, it's not significant. So this number here has only 2 significant figures, 182, as the same as 0.82. Now, luckily, these are multiple choice, so you don't have to worry too much about it. What if I have a weak acid? If I have a weak acid, things are a little bit more complicated. Okay, so let's go one step at a time. So let's take an example of a weak acid, nitrous acid. We are going to be very diligent and we write the dissociation including water. If you write it without the water, from the mathematical point of view, it's not going to change a thing. So we write the Ka. First thing you want to do is write the Ka. Because water is liquid, it doesn't appear. That's why it doesn't make any difference if you include it or exclude it in the equation. In order to determine the pH of a solution, we need to figure out what is the concentration of this guy, because then we can plug it into the formula of the pH. Okay, and so there are different scenarios. They can give you the Ka and ask you to calculate the pH, or vice versa. So we're just going to work on it. Then you have the worksheets to see more example. So we have a solution that's 0.15 molar of HCN, and I just want you to notice it was the same concentration of the hydrochloric acid, so you can see the difference in the pH between the two. The weak acid is going to have a less acidic pH. That kind of makes sense, right? So immediately, so you should remember that this is a weak acid because, sure, it's the title of the slide, but you wouldn't have that in a problem, right? But HCN is not one of those 7 or 6 strong acids. However, even if you don't remember that, I'm giving you the Ka, so that tells you this is a weak acid, because the Ka is a very small value. It's 10 to the minus 10. So first thing you want to do is write the dissociation equation. And then write the Ka, right? Once you have those two, you start doing some reasoning. Now, the best way to approach these problems is to organize the data into a table. The table is called rice or ice table because there is one line for the reagent, that's the R, and then you have one line for the initial value of the concentration, and then you have one line for the change in the concentration, and then the last line is for the concentration at equilibrium. Why do we have to do this? Because the concentration I'm giving you, 0.15, is the concentration initially. So imagine like I haven't yet made the solution. I have the HCN in one hand and I have the volumetric flask in the other hand. I have not yet poured the HCN into the solution. However, the numbers you have to plug in here, and this is in particular, the H plus is the number you want to calculate the pH. Those three numbers needs to be the concentration of equilibrium. The concentration of equilibrium are not going to be the initial concentration. They're going to be different. That's why you need to do some math. This, unfortunately, is not like the strong acid where those concentrations were the same. Here is going to be totally different. You kind of know that by the time you reach equilibrium, the amount of H plus is going to be minuscule. It's going to be really small. While for the strong acid, it was going to be equal to the amount of acid you were dumping in the solution. While here it's going to be much, much less. Okay, how much less? That's what we're trying to figure out with the table. So let's figure out the initial. The initial would be what you have at time 0, when you haven't yet, when water is still here and the acid is still here and they haven't yet met. Therefore, the solution, the concentration of the acid is going to be the 0.15, the total. The water, we really don't care. It's irrelevant, so we just don't even bother writing that. It's constant. At the very beginning, the concentration of the H plus and the Cn minus is going to be 0 because the dissolution has not yet started. Now, the next things you want to figure out is in which direction the equilibrium is going to shift. Okay, so the proper way to do it would be to calculate Q. If Q is too small, or if Q is too big, or if Q is equal to K, then you know in which direction it's going. But it doesn't take rocket science here to figure out that no matter how small is Ka, is not 0, right? So there's by the time you reach equilibrium, you're going to have a little bit of H plus and a little bit of A minus. So if you start from 0, it can only go up, right? So the reaction is going to go in that direction. If you calculate Q is going to be 0 divided 0.15, so it's going to be 0. So for sure it's too small. The reaction needs to move towards the products. So now that we've figured out the direction in which the reaction is moving, we can figure out how much the concentration are changing. We don't know the number, let's call it X. Okay, so the concentration of the HCN is going to decrease a little bit because some is going to dissociate. So it's going down of an amount of X. The minus sign is because it's going down. That very same amount is going to be the amount that H plus is going up because there is the same coefficient in front of HCN and in front of H plus. So they are in a 1-to-1 ratio. So the H plus is going up of plus X, and the Cn minus is going also up of plus X. Therefore, at equilibrium, I will have left 0.15 minus X of HCN. And the concentration of the H plus and Cn minus is going to be identical, and it's going to be X. And that's my X, the one that I want to figure out, because is the one here that I need to plug into the pH calculation. So what I can do next is substitute the value at equilibrium. So these are the values that are relevant. I'm going to plug them in here, right? So I'm going to, this is the value given, 4.9 times 10 to the minus 10 is given. On top I have x times x, so is x squared, and at the bottom I have 0.15 minus x. Now, unfortunately, when I rearrange this, I end up with a second degree equation that requires to be solved the quadratic formula. Now, fear not, the quadratic formula will be given in the cover of the exam. Nevertheless, it's a royal pain to have to use it. I personally, I don't know, I just have this strong dislike for the quadratic formula, maybe some trauma in middle school. So anyway, you can solve it, and as usual you get two solutions, right? Because there is a plus minus here. Now, one of the solutions is positive, the one in red. The other solution, the one in black, is negative. Now, just because math tells you that there are two solutions, it doesn't mean that they both make sense. We kind of know for a fact that x is a positive number, if we take the negative solution, this would become minus 8, whatever. So it would become positive. That would mean that the HCN is going up, like we are creating HCN out of nowhere, so that just doesn't make sense. So we're going to eliminate the negative solution. So we've seen that to solve this problem, we end up with a second-degree equation that requires the quadratic formula. And I'm trying to find a shortcut that allows me to avoid that and to make the algebraic resolution faster and simpler. So let's have a look at the here at the formula that will come up after substituting into the formula of the Ka the values that we have calculated for equilibrium. So we kind of know the expectation is that x is going to be a very small number. So if we take away x from 0,15, that should be a minimal change in that denominator. So maybe we could simplify our life and assume that 0,15 minus x is almost, let's say, the same as 0,15. We kind of solved the problem in the other slide, in the former slide, and in fact the value of x was really small, and if we do the subtraction and apply the proper sig fig, we would end up rounding to 0,15, so it doesn't really change that much, right? So if we make that simplification, we can rewrite the formula in this way, and that's much simpler because once we rearrange, all we have to do is extract the square root. That's going to be much faster. So we end up once again with two values because you got two solutions, but as I said before, only one makes really sense, that is the positive one, and you can see that we come up with the very same solution that we got in the former slide. So our simplification did not introduce any error in the calculation, but saved us a lot of time, and that could be very precious time in a setting like an exam, or especially the final, right? So we are really happy about that. Now we can calculate the pH as the logarithm of that concentration. Now, as a general rule, you want to start by using this simplification. In this case, we knew it was okay because we had the actual result to compare. So what actually happened here was we went through the whole resolution using the quadratic. Then we did the solution with the simplification, and we figured out that the result was the same, but that's not much of a shortcut. Is anything, is making us working twice the problem, right? So if let's imagine I didn't go through the quadratic before, and I just did the simplification without any pre-existing knowledge or about what the result was supposed to be. How would I know if I have introduced a significant error or not, right? The reason in this example that I picked, we came up with the same result was that the value of the Ka, that's this, was significantly smaller respect to the concentration. So it's all in the balance between how much is the concentration of the acid and how much is the pKa, how much is the Ka of the acid, the relative value of those two. So in general, the best way, the smartest way to proceed is assume you can do this simplification, even if we are not sure. And do this simplification in here, that is like assuming basically that the concentration in equilibrium is the same as the initial concentration. We know that's not the case, but we assume that the decrease was negligible. And then after you're done and you obtain your result, we need a way to check if this result is acceptable. And this is what is called the 5% rule. So the check is done by using the 5% rule. So to recap, if you're given a problem where you have to calculate the pH for a weak acid at a given concentration, start by assuming that you can do the simplification and that you can just use the initial concentration as concentration at equilibrium, in which case the formula becomes the one that you can see in this slide, and that means that the math is much shorter and you can save time. Once you have figured out what you solve for H plus, or you solve for the concentration of the H plus, you need to check that the percent ionization is less than 5%. That's where the 5% rule comes, that the percent ionization should be less than 5%. What is the percent ionization? The percent ionization is the percentage of the H plus concentration respect to the initial concentration of the acid. So in our case, we would have to take the result for the concentration of the H plus at equilibrium, divide by the initial concentration of the acid, the total concentration of the acid, multiply by 100, and we get that in fact it was way below 5%, so we were good. If we would have been unlucky and the result would have come up larger than 5%, the consequence was that we would have to take all our work, throw it in the garbage, and restart from scratch using the quadratic. Now, that's not much of a time-saving shortcut, in my opinion, because you know, the risk is that you have actually to do the work twice and therefore wasting time. So some people would just go with the quadratic from the beginning, just to say better safe than sorry. However, there is a way to know ahead of time if it's safe to apply the simplification, and it's a rule of thumb that comes from doing backward the math, starting from the 5% and go backward and see what should be the relative value of Ka and Ha, so that I end up with less than 5% ionization. So the rule is that the concentration of the initial concentration of the acid should be at least 400 times larger than the Ka. If that's the case, you can just go ahead and use the simplification. In an experimental setting, the concentration of the equilibrium of the H plus, it's easy to determine experimentally because it's related to the pH. So you could just, if you have a pH meter, that's an instrument that will tell you the level of the pH of the solution, and you go 10 elevated to the minus pH, you get the concentration of the H plus at equilibrium. The initial concentration of the HA, unless you know because you made the solution, so you know how much you put in it, it can be determined by a titration, because a titration would measure each and every molecule of HA. So as you can see, applying our rule of thumb, we could have seen immediately that we were safe using our simplification. So the stronger is an acid, you would accept that you have a larger acidity constant, Ka, but you also would have a larger percent ionization. Like if you go at the end of your book, you would see, and in every book, you would see tables that gives you the value of the Ka, but you wouldn't see tables giving you the percent ionization. So if both are related to the strength of the acid, how come we typically use the Ka to quantify how strong or how weak an acid is? That's because the Ka, as the name suggests, is a constant. As long as you don't change the temperature, Ka is not going to change. Instead, the percent ionization is strongly influenced by the concentration. So if you change the concentration of the acid, the percent ionization would change. In this graph, you can see that the higher is the concentration of the acid, the lower is the percent ionization. So if acid is diluted, it tends to have a higher percent ionization, and that may seem totally counterintuitive, but there is an explanation for that. So let's imagine that we have the same acid, In one instance is 1 molar, in the other instance is 10 times more diluted, is 0.1 molar. So obviously the molarity for the diluted one is smaller. The Ka, being a constant, does not depend on the concentration. It depends only on the temperature. So if for both the temperature is 25 Celsius, we would have the very same equilibrium constant. That for this example, acetic acid is going to be 1.8 times 10 to the minus 5. What's going to be the pH? The pH of you would expect that the pH is going to be more acidic for the more concentrated solution. So you would expect a lower value of pH for the concentrated one and a higher value of pH for the diluted one, right? And that's what in fact we have. 238 means that the concentration of the H plus is higher than for a solution in which the pH is 2.88. This is because it's calculated through minus the logarithm. The concentration of the H plus that can be calculated by elevating 10 to minus the pH of the solution. So we can calculate the concentration of the H plus based on this value, right? It's going to be in fact higher, about 3 times higher for the concentrated one, right? So despite the fact that is 10 times more concentrated, the concentration of the H plus it's only 3 times higher. That's because it's a weak acid. So the percent ionization is going to be, so if you take the value of the concentration of the H plus and you calculate what percentage is this out of the molarity, in this case is 0.1%, in this case is 1.32. So the percent ionization is higher for the diluted one. The concentration of the H plus is still lower, but it's going to be a higher percent because it's calculated respect to a smaller number. Okay, so the two things are not in contradiction. So how can you kind of make a sense of this? So you can reason in terms of collision theory in a way, right? So the more concentrated is the HA, the more the solution is going to be acidic. So you're going to have more of this and more of that. That means that the probability that they collide and run into each other in the solution and reconnect to reform HA is going to be higher. That's why they have a harder time dissociating. Even if the absolute value of the H plus is going to be higher, the percentage that is ionized is actually going to be smaller. Or you can have a mathematical approach to it. So let's imagine we are diluting by a 10 factor. That means that all the concentration are going to be 10 times smaller, right? So you're not at equilibrium anymore because you have changed the concentration. So you can calculate Q. So on top you have this that's been diluted 10 times. This has been diluted 10 times. So it's going to be the difference is going to be a 100 factor, while this is going to be 10 times. So here you have a 10 factor. So that means that the numerator has been affected more than the denominator. So Q is going to be too small. That means that the equilibrium needs to move to increase once again the top of the fraction. So you want this value to become larger. That means that the reaction needs to move this direction. So because you have diluted, you are pushing the equilibrium towards the products. That means more dissociation. Let's see the example of ammonia. If I put ammonia in water, ammonia is going to be the base. Is going to accept a proton from water, so water is going to be the acid, and after accepting the proton I'm going to form ammonium ions, so that's going to be the conjugated acid of ammonia, and OH minus is going to be the conjugated base of water after water loses its proton. So because this is a base, the equilibrium constant describing this equilibrium is going to be called Kb, and it's going to be written with the usual rules. So we put the two products concentration on top, the concentration of the reagent at the bottom. Water will not appear because it's an heterogeneous equilibrium and water is a liquid. However, I could also go to the stockroom and get a bottle of ammonium chloride, NH4Cl-. That would be an acid. It's an acid because it's the conjugated acid of ammonia. So it could donate its H+ to water. Water would be this time a base. After donating its H+, ammonium turns into ammonia. That's the conjugated base of ammonium. And water, after accepting the H+, turn into H3O+, that is the conjugated acid of water. So for this one, I can write a Ka. Same rules as before. So because these two reactions are describing from different perspectives the same conjugated pair, ammonium and ammonia, the Kb and the Ka have a lot of shared species formulas. So if I multiply one times the other, I can make a lot of simplification. So I take the Ka and I multiply by the Kb, and I can simplify ammonia here and ammonium. And so what I'm left with is just the H+ and the OH-. So the product of the Ka and the Kb for conjugated pair of acids and base is going to be equal to the product between the H+ and the OH-. That is, as we have seen, a constant value of 10 to the minus 14. So this means that Ka and Kb are inversely proportional. The larger is the Kb for an acid, the smaller is the Kb for its conjugated base. And the larger is the Kb for a base, the smaller is the conjugated Ka of the acid. So because those are measures of the strength, means that the stronger is an acid, the weaker is its conjugated base. And the stronger is a base, the weaker is its conjugated acid. So here you see this relationship exemplified for several couples, for several conjugated pairs. So for example, here in the middle, you can see that you have carbonic acid and bicarbonate, and the product of those two values of Ka and Kb give you 10 to the 14. So if I go on this side where I have a very weak acid, HPO4 2-, and I know it's very weak because the Ka is very small, the conjugated base, that is phosphate, is going to be quite a relatively strong base, and vice versa here for let's say HF, I have a relatively high Ka. Consequently, F- is going to be a quite weak conjugated base. So when I consider strong acids, like sulfuric acid and hydrochloric acid, when they dissolve in water, they are completely dissociated. So each and every molecule of ACl turns out to be H3O+. And that's going to be the same regardless if I have HCl or HSO4. So they are so strong that I cannot really differentiate between them. It's a sort of a ceiling effect, because the actual acid that I have in solution is going to be H3O+ for all of them. So this is what is referred to as leveling effect of water. So somehow the solvent determines my ability to distinguish between the relative strength of several acids.